Welcome back.
So given a continuous random variable with a distribution function Px, density function is a function. Density function, I will denote it with small p and an x to denote that the x is the underlying random variable. Okay, this is my notation. Px, it's a function from the range of the random variable, range space of the random variable to R plus. It's a non-negative function. Remember that density functions are simply non-negative functions. They are not bounded between 0 and 1. I will tell you, I will talk about the properties of this in a while. It's a function which is from x to R such that if you evaluate this function at some point x, this will give you the, I will write it the other way around. So if you take the distribution function and evaluate it at x, this is equal to the running integral of this particular function. This is the definition of a density function. Okay. Now by definition, please note that suppose you evaluate the density function at a particular point, what does that give you? It will give you a positive number, right? It will give you a positive non-negative integer, but that does not correspond to probability. Please remember this. It's a trivial mistake that a lot of people do. Evaluating density function at a point is not a valid probability measure. Come again? No, you can evaluate it at a point. See, no, it will not be 0. It will evaluate to a particular value, right? You take the Gaussian density function, plug in a value to the x, you will get some value. Yeah, probability is 0. That's what I am trying to say. See, you can evaluate, two different things. Density function is a function. You can evaluate the density function at a point, but that does not give you a probability. That's all I am trying to say. If you integrate the density function over a range, by definition, it is a valid probability measure, because integrating a density function over a small range corresponds to a distribution function, and distribution function is a valid probability measure because it's a push forward measure. But evaluating the density function at a particular point is not a probability measure. I mean, one trivial example that I always give people, see, when I talk to people and conduct interviews, etc. This is one trap that I throw towards people. They'll say, well, this thing, Gaussian density, it's pretty easy, right? I mean, you can actually, it's bounded and therefore value can be interpreted. People interpret this as probability. So then I'll ask them to write down the density function for a uniform random variable that is uniform between 0 and half. What is the density function for a uniform random variable that's uniform between 0 and half? It is 2. So now it's always more than 1, right? So how can you interpret that as probability? If you evaluate the uniform density of uniform random variable between 0 and half, it will evaluate to 2 at all points. But probability measure, if you remember, is a function that is bounded between 0 and 1, and this is one example where you can clearly show that the evaluating density function at a point does not give you valid probability measure, but integrating it would. Okay. However, the value or the evaluation of the density function at a particular point is called a likelihood. This is the nomenclature that people use. Okay, anyway, I'll use that nomenclature later. The reason I define density function is most algorithms, okay, operate on density functions, not on distribution functions, just for mathematical ease. There is no other reason. And all of you already know that not all random variables can have density functions. So there can exist random variable where the density functions are not even defined. See, this is for the case of a continuous random variable. For the case of a discrete random variable, evaluating density function is a valid probability measure. Okay, you actually, for a discrete random variable, you can interpret the the density function. It's not called the density function, it's called the probability mass function. Evaluating the probability mass function at a particular point is a valid probability measure by definition. not for the continuous. That's why I defined it for the continuous random variable. In general, we will, I mean, most of our data can be interpreted as continuous random variables. That's why we will be working with density functions. So we have to change our problem. I said given D, estimate the distribution function, right? Now I'll say given D, estimate the density function. I'm assuming that all the data that we will be having can be modeled using those random variables for which the density functions are well defined. That's a fair assumption to make, because most well behaved random variables will have density functions defined. Okay, so we will work with density functions, from now on we will work with density functions. Okay, so all these problems, right, now will be, instead of estimating the conditional distribution, we will be estimating the conditional densities p of y given x and p of x and so on, right. So please note the change in notation. If I write p with, you know, 2 lines, it's a distribution function. If I write it with 1 line, it's the density function. And throughout the course, rest of the course from now on, I'll be working with density functions, not with distribution functions.
It's not in the real world. There can be sort of distributions which can't be described in good mathematical functions.
No, that's not what I'm asking. That's not what I'm saying. That's a question that we'll be seeing later. See, all I'm saying is, in real world, all data that we have can be assumed to have valid density functions. That's it. Valid density functions. What I'm talking about is, there are random variables for which the density functions cannot be defined. So I'm saying, we are assuming that all the data that we have, that we get in practice, can be defined, or rather will have, or can be defined using random variables, can be represented using random variables for which the density functions are well defined. That's all. Okay. See, if you people do not know what density functions are, please read up. But yeah, this is what it is. It's another function that is defined from the range space of the random variable x to R plus. They are non-negative functions. The range space of the density function is always positive real numbers, and the definition of it is that it's a function which would evaluate to distribution function at a point if you consider its running integral between minus infinity to x. And this integral, by the way, is not a single integral, right? If it's a d-dimensional random variable that we are talking about, then it's a integral over Rd, usual Lebesgue integrals. Okay. Okay. Right. So I think we have now laid the foundation that we needed for defining the machine learning problems. As I said, it's mostly density estimation problems, conditional marginals and joint densities and so on, given samples from it. So how do we do that? Think about it. It's a non-trivial problem to solve, because, okay, let me write it down. The challenges with ML.
We'll see in the next lecture.